Okay, so let's continue with our revision 2021 MRSM Physics Paper 1. So the first question, which of the following is the imperial units? So imperial units is just the opposite of our SI units, International System of Units. Alright, imperial units is the units that are in British used in the older days, such as inch, okay? So inch is the imperial units. It's one of the imperial units. Inch, pound, gallons, and much more. So they are under the imperial units. And meter is the SI units of our length. Mole is the SI units for us to calculate the amount of substance, okay, atoms, molecules, or particles. And candela is the SI units of our luminous intensity. So the answer for question 1 should be A. Next, diagram 1 shows a displacement time graph of an object that moves towards a target and returns to its original position. Okay, so what is the total displacement of the object? So remember, displacements, okay, you just take the distance, okay, displacement is the shortest distance between 2 points, okay, so this is A and then this is B. So if you move from point A to point B, it is 5m, and then you move back, okay, and which means your initial position is at A and your final position is at A. Then your displacement should be 0. But if you are calculating the distance, then your distance should be 5m. Okay, the total distance traveled should be 5m, but the total displacement should be 0. Okay, so this is your displacement time graph. Okay, so you can observe that the distance traveled, okay, from here, okay, and then it stops for 4 seconds, and then it drives back. Okay, so this displacement should be 0. Okay, because at the final position, the displacement is 0. The initial displacement is 0, and the final displacement is also, so the initial position is at 0 and the final position is also at 0, so the total displacement should be 0. Okay, so diagram 2 shows an object is free falling in 2 different situations. Okay, so which statement is correct to explain the motion of the object when it's moving downward? So free falling, which means your ball, okay, your object is only subjected to your gravitational acceleration, which means there is no air resistance acting towards your ball when your ball is falling. So the answer is your increasing velocity, yes. Okay, decreasing velocity, no, because your gravitational acceleration is acting downward. Your gravitational acceleration is 9.81, and because it is pointing downward, it should be negative. Okay, and because it is pointing downward, so when your object is also falling downward, it should be increasing. But if your ball, okay, your object is throwing upward, opposite to your gravitational acceleration, then your velocity should be decreasing because your velocity is in opposite direction to the gravitational acceleration. So in this case, your answer should be A. Okay, increasing acceleration, no, because free falling is on the object is only subjected to gravitational acceleration, which means there is no air resistance. Then your gravitational acceleration is constant. Decreasing acceleration, no. So the answer for third question is A. Diagram 3 shows a box with mass of 55 kg being dropped from a helicopter at the moment before touching the ground. The velocity of the box is 300 meters per second and it stops after 2 seconds touching the ground. So what is the magnitude of impulsive force acted on the box. So we have the formula F equals to mv minus u over t. Okay, so you just sub in the value. So this force is your impulsive force. Okay, and m is your mass, v is your final velocity, u is your initial velocity. So you just sub in the value 55, and then your before touching the ground, the velocity of the box is 300. Okay, 300 minus u, because being dropped, so initial velocity of your box should be 0, and then 2 seconds. So you will get the answer 55 times 300 divided by 2, you will get speed. Okay. Next, table 1 shows the acceleration value due to gravity from planets Mercury, Mars, Uranus, and Neptune. So which planets produce the greatest weight of an identical object? So we know that the formula for weight is W equals to mg, and m, since your mass is constant, so your gravitational acceleration increase, then your weight should be increasing. So you just choose the greatest acceleration. So should be Neptune. So the answer is A. Diagram 4 shows a planet orbiting the Sun. So which statement is correct to describe the movements of the planets in its orbits? Okay, the planet moves in circular orbits. This is wrong, because according to our Kepler's first law, our planet is moving in an elliptical orbits. All right, elliptical orbits, and our sun is located at one focus. Okay, so this is wrong because it violates our Kepler's law. Second, sector area PFQ is larger than RFS. PFQ is larger than RFS, and the planet takes shorter time to move at RS as compared to PQ. Okay, we look at the final. The planet moves at higher linear speed at PQ compared to RS. PQ as compared to RS. This is true. So the answer should be donkey. Okay, so these two options, B and C, it's somewhat ambiguous because so let's us look at what it states in Kepler's second law. It states that a line that connects a planet to the sun sweeps out equal area in equal time. So which means if your area here equals to area x here, then the time taken, T1 and T2, they will be equal if the area here A1 and A2 is equal. Provided that your area sweeps out by the sun, by the line that connects sun and your planets is equal, then your T1 and T2 should be also equal. But in this case, it didn't give you any hints about your area, or your time taken. So you cannot say that in this case, your PFQ can be larger, can be smaller, and can be equal, because this question didn't give you enough information. So these two options, they just assume that, you see this diagram, you already learned the Kepler's second law, so you just assume that, they are equal, they should be equal, but they didn't give you enough information, so this should be wrong. And planet takes shorter time to move at RS compared to PQ. Again, this question, they didn't give you enough information, so this is also wrong. So the most accurate answer should be donkey. And why is it move at a higher linear speed at PQ is because we already know the time taken for the planets to move from point P to point Q is same as the planet moves from R to S. So you can observe here the distance. The two distance here is P PQ is longer than RS. So you have your distance is equal to ST. All right. So when your T is constant, so when your distance increase, your S should be also increasing. So the distance increase in order to to reach point Q at the same time as R, planets at R to reach point S, the speed will be increased. So the speed here at PQ here will be larger than RS. Okay. So how I remember these facts is that, okay, I will just remember that planets, when it is near the sun, it will gain the energy of the sun. I just imagine like this and tell me that, oh, when the planets gain the energy of the sun, it will move faster. So this is how I remember the fact that the planets will be moving faster at PQ than RS. Okay, so next, diagram 5 shows a rocket being launched to send man-made satellites to outer space. So why does the rockets require a large amount of fuel for launching? So to produce large centripetal force? No, this is not true. So, okay, remember that when your object, okay, so this is your object, it is moving in a it is moved in a circle. So you will have a resultant force pointing towards the center of the circle. So this is what we call this force, is this resultant force is what we call centripetal force. All right. So your rocket is not going to produce the large centripetal force, right? Okay. So just a revision here, your centripetal force, the formula will be Fc, okay, equals to mv square over r. Okay, so this is just a revision. Next, to produce high velocity to move further, no. To overcome the higher mass of your rockets, no. To produce high thrust that enables the rockets to achieve escape velocity. So this is true because the objectives of our satellites is to move to the outer space, and it needs to overcome the escape velocity. Okay, because it is sending to the outer space. It is not orbiting our Earth. Okay, so okay, let's do some revision. So we have two types of velocity in chapter 3. We learned two types of two equations for the velocity. One is linear velocity of the planets, and another is the minimum velocity, the escape velocity, the escape velocity of the object. Okay, so this is your centripetal force, and this is your Earth. Okay, this is your Earth, and when an object is orbiting around the Earth, okay, it is similar to this case you can observe. So when your object is moving around the Earth, orbiting around the Earth, you will also have a centripetal force directed towards the center of the Earth. So this force, it is actually similar to our gravitational force. So our gravitational force, okay, is equals to gmm over r squared, where the capital M here is representing your mass of Earth, and your small m here and this small letter m here is representing the mass of the object. Okay, so you can equal these two formula, you will get mv square over r equals to gmm over r square. Okay, so you just cancel out the m and cancel out the r, you will get v equals to gm over r square root. Okay, so this is your linear velocity, your velocity for your object or your satellite to orbit around the Earth. Okay, so when your velocity, when your object is have the velocity equals to square root gm over r, you will the satellite will orbit in a circle around your Earth. Okay, but if your velocity is smaller than this, then the square root of gmm of r, then your object will fall into the Earth. Okay, and we also have another types of velocity, which is our escape velocity. So the escape velocity, we have the equations v equals to square root 2gm over r. This is our escape velocity. Okay, so when your velocity of the object is equal or greater than your escape velocity, then your object will move away from your Earth. Okay, and if your velocity, okay, is smaller than your escape velocity but greater than your uh, linear speed, the linear velocity, the, which means greater than this, then your satellite will move in elliptical orbits around the Earth. Okay, so some students, they may curious how your escape velocity, how to obtain the equation for the escape velocity. So if you are Form 4 students, you can just skip this part because you haven't learned the integration in maths, which you will learn in Form 5. So for Form 4 students, you can just skip this part, and for those who are not interested in this, how to derive your escape velocity, you can just skip this part because this is out of your syllabus. I just because some students may curious about it and ask. Okay, so I will just continue to show you how to derive. So in order to derive this escape velocity, we will use two concepts. One is kinetic energy, okay, and another is gravitational potential energy. Okay, so our gravitational potential energy, you learned in your PT3 is equals to mgh. But in this case, we cannot use this formula, this equation again, because this is Earth, and then our object, they are far more away to your Earth. Okay, so it is not, the gravitational acceleration is no longer the same. So you can no longer use this equation. So how can we find the gravitational potential energy? Okay, so we know that gravitational potential energy, it is actually the work done. Okay, you see our work done, the formula of work done is equal to Fd, where this is your force, this is your distance. So actually, your G, gravitational potential energy, is derived from your work done, because you can see here mg is actually your force, okay, and h is your distance. Okay, so we just use this equation. Okay, I just draw out the graph. This is your F, this is your D. Okay, and this is your, okay, so the area under the graph, you want to find the area, you will just use here multiplied by here. So it is just the FD. Okay, F multiplied by D. So basically, the area under the graph for the force distance graph is the work done. So here the area under the graph will be the work done. So in this case, okay, we want to, so we learned that you want to find the area under the graph. In your Maths chapter 3, if I'm not mistaken, you know that you integrate the equation, okay, you will get the area under the graph. Okay, so in this case, okay, this is how your force to distance graph, you will get a graph like this, a curve here. Okay, this is what you get if you are measuring the force, gravitational force, okay, to the distance when your object is far more further from your Earth. Okay, so this is your gravitational acceleration, gravitational force, and this is your distance. Okay, so this is what it looks like. So your equation here will equals to F equals to gmm over r squared. This is your formula for gravitational force. So when you want to find the area under the graph, so you just integrate the value. So you just integrate, okay, gmm over r minus 2 dr. Okay, so because the definition for the gravitational potential energy is that the force, the energy required, your energy when your object is moved by external force from infinitely far away to the distance, to the position where the object are. So it is moved from infinity to the r, okay, to your r at here. So this is your r at the surface of the Earth. Okay, so you just integrate it. So this is 0. Okay, this should be 0, and you will get your gravitational potential energy. The value will be negative 2 gm over 2 gm over r. Okay, so this is how you get your gravitational potential energy. So when you want to achieve the escape velocity, then your escape velocity have to overcome the gravitational potential energy. So basically, your net force should be 0, right? Because your F net force should be 0. F net equals to 0. Okay, so net force basically just the summation of your force. Okay, so you have mv squared, your kinetic energy should overcome your gravitational potential energy. Okay, 2 gm over r, and you get 0. Okay, so finally you will get v equals to, okay, you cancel out gm over r2 and then square. So this is how you get your escape velocity. All right, so the final answer for 7 should be dot D. Okay, next, number 8. Diagram 6 shows a man is pouring water into his car's radiator to control the temperature of an engine. Assuming no heat loss to the surrounding, thermal equilibrium is achieved when all the water vaporized. No. Okay. Engine temperature is higher than water temperature. No. Okay. Water temperature is equal to the engine temperature. Yes, the answer should be C. Heat energy in the engine is equal to the heat energy in water. This is not true. So let's understand what is the meaning of thermal equilibrium. Okay, so initially when your two objects, okay, object A and object B, they have different temperature, then the heat energy transfer will occur at different rates. But when your temperature it becomes the same, okay, then the heat energy transferred from A to B and B to A will occur at the same rates, okay, at same rates. So this is what the thermal equilibrium means. Okay, so the keywords for thermal equilibrium is, okay, the first one, net heat transfer equals to 0. Net heat transferred equals to 0. Okay, and the temperature is equal, the temperature is same, so rate heat transfer is the same. Transfer is the same. Okay, So net heat transfer, the net here means that, okay, this is your object A and this is your object B. Okay, net heat transfer is that, okay, here the heat transfer from A to B is equal to from B to A. But if your object is occurred like, okay, A and B, okay, maybe 2 joule of energy is transferred to your A and B from your A to B, and 1 joule of heat energy is transferred from B to A. So this is, we cannot say that. So the net heat transfer here will be 1, okay, because 2 joule from A to B and 1 joule from B to A, okay, then your net will be 1 joule. But here you can see here 1 joule of heat from A to B and 1 joule of heat from B to A. So we say that the net heat transfer is 0. Okay? Okay. So this is not true, this is not true. So why the heat energy in the engine is equal to the heat energy in water? Why this statement is wrong? Okay, because, okay, we know that the heat energy, the formula, the equation is Q equals to mc theta. When your theta is constant, okay, your temperature is constant, okay, your temperature change is constant, your temperature is constant, but your C and your M for different material, they are different. So this should not be the answer. Just remember that in an object, okay, if the temperature is same, that doesn't mean that the energy inside the object, the heat energy of the object is the same. Because, okay, just for example, okay, this here we have 2 types of container, okay, this is 2 container, and then the water, they have the same height, okay, the water level have the same height. But this doesn't mean that they have the same volume of water, right? Okay, this is because the heat capacity is different. Okay, so the answer should be C. Diagram 9. Diagram 7 shows the sea breeze phenomenon. Okay, so when you saw this diagram, you know that this is related to heat capacity. So C, okay, so heat specific, so the answer should be donkey. Okay, specific latent heat, we only use this concept when we involve the change of state of substance from solid to liquid, okay, or from liquid to gas. We will use this concept when involving the change of state. So sea absorbs more heat than land during daytime. This is not true. Okay, sea releases heat faster than land. No, this is also not true. It should be this should be not true. This should be slower. Okay, it should be slower. Okay, so question number 10. Diagram 8A shows water is being heated using a heater. A bimetallic thermometer is used to record the temperature of the water. Which of the statements below shows the correct explanation for the situation above? So the process of water changes to vapor is called condensation. So from liquid to vapor, this should be evaporation or boiling. But in this case, should be evaporation. Okay. The heat received remains the same throughout the experiments. This is wrong because we know that Q equals to mc theta. Okay, your temperature is maintained constant. Okay, but you can see here the specific heat capacity for same liquid should be also constant. They are same, but the mass here, they are changing. Okay, the mass is decreased, so the heat energy supplied should not be the same. Okay, the heat supply is used to break the bond between the molecules. Yes, this is true. If this is water, is this a water? Okay, it's the yes, this is water. So if the water here just you learn in your chemistry, so the bond broke here is your hydrogen bond. Okay, so this is true. The volume of the water decreases as it changes to vapor due to continuous heat supplies. This is true. Okay, because your water molecule gain kinetic energy, and the kinetic energy is enough to overcome the bond. So heat energy, so it's vaporized. The heat energy is converted to the kinetic energy between the kinetic energy of the water molecules. All right, so the answer should be 3 and 4. The answer is C. Okay.